Hi everybody. Well, today let's continue our discussion with the address mode. And last time we discussed the first 4 different address mode, and we discussed about the adherent address mode, immediate mode, the direct mode, extended mode, and we mentioned the direct mode and extended mode. They work quite similarly. The main differences is the address. Extended mode has wide address, has double size of address. All are the same. Well, today let's continue with the rest 2, index address mode and the relative address mode. And these 2 address modes are a little bit more complicated than these 4 we discussed last time. But they are very, very useful. Now, so we finished all the first 4 modes with some examples given last time. Immediate mode, the direct mode, extended mode. Now for the index address mode, so I'm pretty sure we already had some examples before. It's mainly to use X and Y, these index registers. Okay, mainly to use X and Y, Okay, yes, that's quite easy. Okay, we add an offset to the base value of index register X or Y. Then it's very easy for us to go through a list of data items that are stored in memories. So every time each time we go access 1 at a time. Okay, so in this case it encounter a task to find the location 0 from list of items. So we start from 0. That's what we need to save its value in X or either Y. Then we keep adding an offset value to either X or Y, like this. So the instructions of index address mode in general allow the programmer to use one of the index registers. Okay, here I mentioned this X or Y. So this 2 is X or Y. Okay, as pointer, we're moving along list. So we keep track of the current position in the list. Okay, like this. So it's very easy for us to process all data as one in the same way. So we form an effective address by adding the contents of the index registers, stack pointer, or the program counter with offset value. Like this. So it's not only to X or Y. We can also do a similar job for stack pointer, here SP or program counter, like this. So it's very useful, especially if you need to process a large number of data. So we have flexibility to treat the effective address as a variable, like this. Then we can also modify the contents of index register, a stack pointer, or use the program counter to change effective address. Now, because X or Y points to a particular address, and when we have a large number of data, sometimes we move forward, sometimes we move backward, we process the data. In this case, the offset value we add into the base register is X or Y in general can be either positive or negative value. So therefore, the offset value got to be a some number. Okay, some number, so either is positive or negative. Then when we added this number into X, Y, so that makes us move backward or forward, like this. Of course, when you program, okay, the offset can be any number systems. So we can either using hexadecimal or binary or decimal or whatever we like. So there's no limitation. Okay. So in general, most people prefer to use decimal because it's easier for us to know that. So it can either hexadecimal or decimal or binary, like this. Now, no matter offset is decimal or binary or hexadecimal, okay, this type of address mode offers 3 different options for the offset length. Okay. In other words, the offset size can, if you represent in binary, in general, offset of length can be 5 bits or 9 bits or 16 bits long. So in general, we use one of them. Okay, of course, if the range we need to go is very small, then we use 5 bits. If relatively larger, then we use 9 bits. If we need to go to move forward or backward to anywhere, we make offset length to be 16 bits. So let's start discussing with each of these options. Okay, let's start with 5-bit. So in other words, we make the offset to be 5-bit constant. Okay, with some people they simply call this type option to be 5-bit constant offset indexed address mode. So in other words, this is still indexed address mode, but the offset value is 5-bit. So it's 5-bit constant offset. So the value we put in the 5 bits is offset value. We added this value, no matter it's positive or negative, into the base value of either x or y. Okay, like this. In this case, because it's only 5 bits, the total range is only 32. Total range is only 32. So either in this case, is value range from -16 to +15. This is the range we have. Okay, the base index register can be either x or y or stack pointer or PC, but the range is only from -16 to +15, including 0. So if we include 0, in total we have 32 numbers. We have 32 numbers. Now, so the range is quite very small. In other words, if you use this 5-bit constant offset index address mode, then the range, the numbers, okay, you need to process in general, okay, is got to be less than 32. So because those are values stored in memory, but the memory range you can go is only within 32. So the range of the offset is quite very short. It's very short. However, this one is the most commonly used one. So the 5-bit constant offset index address mode is one of the most often used offset value for the indexed address mode. Okay, because this range is very small, this is going to make our program very, very shorter. Okay, is much more manageable. So this is called a 5-bit constant offset indexed address mode. But is one of the option. Is one of the indexed address mode. Only things make offset to be 5-bit. So let me show you some examples of the 5-bit constant offset indexed address mode. Okay, LDAA 0x. This is very simple. Okay, here the offset is 0. Okay, this is offset. Okay, 0. Okay, so this one load the contents of memory location pointed to by index register X into accumulator A. So it's nothing but a load the value where X points to in memory into A. So here offset is 0, so we added 0 into X. Okay, so it's so easy. Now let's check another one. This one is STAB. We store the value of accumulator B into a memory location. But what's our location? The address of location is specified by X and the offset. X is whatever X is. That's how we load a numerical value into X to initialize the index register to make X points to there. But now offset here is -8. Is a decimal number. This is a decimal number. Okay, it's -8. So we gotta add -8 to the value of X. That gives us location where we want process. That's where we hope to store our data of accumulator B in memory. Okay, so the address contains our data of B will be the value of -8 added to the value of X. So which is equal to the contents of index register X minus 8. Now, so here -8 is not more than 5-bit because -8 right here is in a range from -16 to +15. Is in this range, so it's with 5 bits. So this is a very simple example of the 5-bit constant offset index address mode. Let's check out another one. It's 9-bit constant offset. Everything's the same. The only difference is what? The offset value become much larger. So it can be much larger. So its range is much wider. So it's 9 bits. If it's 9 bits constant offset, okay, that's the value we add into either X or Y. Depends on we use X or Y. Because it's 9 bits. So if you take what? If you take a 2 to 16, if you take a 2 to 9, that gives 512. This is the total range we have. Then what? But we are allowed to have both positive and negative. So we have 0 included. So this is going to give us a range of this. From negative 256 to positive 255. With 0 here, 0 is included here. So in total we have what? We have 512, range from negative 256 to positive 256. So this value, okay, we have that we should add into X or Y. Okay, so we can get a new address. So in general, the value X or Y or SP or PC they include, we call the base register. The base register. That's what the base value contains. That's what we have here. That's the value where we add to. Okay, this value does not have to be X or Y. Can be stack pointer or can be a program counter. But for program counter in general, we don't write on program counter. Okay, because it's the value already there. That depends on what's the value there for a program. So this shows a 9-bit constant offset index address mode. Another one, okay, is 16. But before I show you 16-bit constant offset index address mode, let me show you a couple of examples for the 9-bit constant offset index address mode. FF we have here. Go this one. This specifies what? It forms effective address. So X contains base value, but the value we add right here, we add into to X is FF. When we convert it, when we write on all boundaries on all the 1. Yes, all 1. So this is surely in the range from negative 256 to positive 255. Okay, this value is equal to positive 255. Okay, so it loaded the contents memory location located at address, which is equal to 255 plus the value in X in X. Okay. The next one is what? This time we change offset here. So right here for the first example here, I show you the offset here is hexadecimal. This one is hexadecimal. But when I show this one here, we got this one we use Y, but offset here become what? Become decimal. So it's negative 20. Okay, it's negative 20. Okay. When the negative 20 is also fall into the range from negative 255 to what? To positive 255. From negative 256 to positive 255. Now, if you try to take a look at this example, and compare the one of the 5-bit offset, if you compare this one with this one, okay, 5-bit offset, the range value is only from negative 16 to positive 15, and here we have negative 20. Negative 20 surely is beyond this range, so we have to use 9-bit constant offset. Okay, so 5-bit constant offset is not going to work. But however, when you program in general, okay, and we are not asked to specify this is 9-bit constant offset or this is 5-bit constant offset. Okay, and so whenever you just program it. You don't have to specify. You don't have to say explicitly say that this is 5-bit constant offset or this is 9-bit constant. Okay, you just specify whatever the value we have. Then automatically it will make the constant offset. Then in addition to 5-bit and 9 bits, as I mentioned, we also have 16-bit. 16-bit constant offset values. This one is what? Because much wider. Okay, it can go to anywhere. Because if you have 16 bits, then what? We have 2 to 16. That's going to give a range 65,536. Okay, that's going to range from anywhere. Okay, of the whole memory systems. This goes to 64K baud memory. We can go anywhere. So we add this value to the value X. We can go anywhere over the whole memory systems. But the way it works out is absolutely the same as 5-bit and 9-bit. So this is the type of the what? We add a constant offset value to the base value of register X or Y. So it's constant offset. So you specified explicitly what's the value offset you add to X or Y. In addition, one of the special type of indexed address mode is called a indexed indirect address mode. This is interesting, and we have never covered this before. It's indexed indirect address mode. So what we keep talking about right here is the 5 bits or 9 bits or 16 bits. They all simply called a constant offset indexed address mode. But the one I here show you is indexed indirect address mode. Okay, this is mainly designed for 16 bits. For this type of mode, something interesting is what? The result of addition of the base register of the value of the base register with offset is not that's not the data of address. That's the address of address. So we go there. So we take the summation of offset with base value of register. That gives the address is similar to the constant offset I just show you. You go there, you go to this new address, but whatever in this memory is not the data we need for instruction. You go to this new location, you go to this memory contains address. You go to another location following this address. That's where you get data. So we simply said this type of indexed indirect address mode adds a 16-bit offset to the base index register to form the address of a memory location. That contains a pointer. We call it pointer. So you go there, a new location, you get a pointer. Then you point to another location. That's where you get our data. So one more step. That's why I call it indexed indirect. So whatever I show you right here on this slide, they're all what? They're all indexed the direct address mode. That's where you go there, you get data. Okay. So in order to distinguish between the indexed indirect address mode and the indexed address mode, for the indexed indirect mode, we add a bracket. We add a square brackets, for what? For the offset value and the value of X or Y. So for the address, for the operand field, we add a bracket. This can show the difference between the regular indexed address mode and indexed indirect address mode. So let me show you an example. We're similar to this one. We're similar to this one. It's very similar to this one. This is 9 bits. Similar to this one. LDAB -20 to Y. Now if you put this offset and X or Y inside of the square bracket, then that's going to make this instruction to be in indexed indirect address mode. Like this we have. So we have 10 and X inside a square bracket. This means what? We make it to be indexed indirect address mode. So no matter is indexed interactive mode or is regular indexed address mode, X is always contains the best address of table or pointer. Yes, so we assume now X contains value as 1000. That's initial value that we loaded into X. So now that's where we make X points to. We assume now X contains value 1000. Now right here, similar to the regular indexed address mode, can we add 10 to value of X? Okay, that's going to give us a new address. That's for sure. So if you add 10 to the 1000, then we have a new address called 100A. Right? Yes, this is a new address. So if you have regular index address mode, this is where we get data, and we loaded that value into A. That's what when we have regular indexed address mode. But for indexed interactive address mode, because here we have square brackets, so we have this part. Let me show you here. Because we have this, that's going to make this instruction to be indexed interactive address mode. So we had a value 100A, then so we go to a new location whose address is 100A. We go there, we take the value at this location. Okay. Assume now the value at this new location is 2000. So for the regular index address mode, 2000, that's the value we need to load into A. Okay, however, because this is the indexed interactive address mode, so the 2000 serves as another address, serves as address again. So we need to go to a new location whose address is 2000. We go there, we get that data, we load it into A. So here, the contents of location 100A, which is 200, serves as another address. We need to go to another address, which is 200, to get data from there. We load that value to what? To accumulate A. Yeah, like this. So whatever the value at this location at 200, we load it. Yeah, so if I simply draw this one something like this, if I simply draw this one like something like this. Okay, assume now this memory here. So we have address here. Yes. Now assume now this is address here. This is address now. This is address 100A. So this count here we go gives to what? 100A. Okay, this is what? The summation. This is a result of summation. Okay, yeah. So if the value right here in this location assumes 200, assume now is 200. Assume now is what? Is 20 and 0. 0. Right here, this addresses. Okay, this is the address we have. Okay, now, so then we could do 200. Okay, so yeah, this address we have now. This one we have 100A, and we have 200. So for the regular index address mode, 200. That's the value we load into A. Right? Yes. That's the value we load in. Right now we have indexed interactive address mode. So when this only serves this value is only serves a new address. So assume now this is address 2000. So when we go to this address 200, same address, we get this data. We load this data into A. So it's one more step. So it's called the index interactive address mode. So one more step. So that means that what? The data we got from regular index address mode actually is address. of the final data. That's where we go, we get the data. So now we had one more example on page 52 of textbook. See the figure 2.7. I want you guys to read by yourself. So if you turn to page 52 and you see the figures 2.7, that gives us what a very clear explanation. But here, instead of a numerical value for the offset, they changed the value of d. But same. So here it's nothing but what depends on what's the value of d. That's the offset we add into x. Then we have new address. We go to that address, we take the value at this new location. This value serves as another address. We go to another step, go to a new location following this address. Whatever the data in this new location is the value we load into A. So this is pretty much information for the index address mode. So we have regular constant offset, and we have index indirect address mode. So I want you guys be clear. So the only special is what when we run a program, okay, if you hope to use indexed indirect address mode, then we add the square bracket, as I show here. We add square bracket here like this. Don't forget this. That make it this instruction to run in the index indirect address mode. The last address mode is the relative address mode, and I'm pretty sure we already saw some instructions running in the relative address mode. So relative address mode is mainly designed to work for the branch instructions. When we discussed the branch instructions a long time ago, and I already mentioned this. So relative address mode is only work with branch. So in general, this type of instructions, so the instructions running in the relative address mode, it follows branch instruction. Or yes, I should say they work together. Okay, so where we go, okay, so where's the new location we should go? We jump there to execute. Okay, it's specified by the value here. Okay, afterward as a part of branch instruction. So in general, this type of instruction, okay, they change the program counter value. They change the value of program counter. So that leads us, if the value of program counter is changed, that's where we should go to execute the new instructions. Because what? Because wherever CPU go is always consult the program counter. If the program counter changed, okay, like have offset, or in other words, what? If it's not sequential, then that's where we go to a new location. Okay, so it computes effective address by adding the signed offset to the contents of program counter. The program counter value should be known at that time. Then what? Then depends on what's the offset value we add to it. So it's similar to the index address mode. Okay, the offset can be signed or is signed. It can be either positive or negative. So if this value is a numerical value, then we add numerical value to program counter. We sometimes in order to make it easier, we use label. We just use label. Instead of using numerical value, we use a label. So we simply we add a label. The label represent to the program counter value. That's where we should go. Now remember when we discussed the branch instructions, okay, we have short branch, we have long branch, we have conditional branch, unconditional branch. I remember we had a very detailed, very good discussion. No matter it's short branch or long branch, they all can run in the relative address mode. Okay, I remember I mentioned very clearly what's the differences between short branch and long branch. Short branch and long branch, the main difference is where you can branch to. So if you have short branch, that means what? Okay, the range of machine code you can jump to is relatively closer to you. So we simply say the distance from where you go and now is quite short. Okay, it's quite short. In general, for short branch, okay, the offset bits is only 8 bits. Okay, or we said what if offset is what specified by 8 bits, then what we call short branch, because it's 8 bits. So if you take a 2 to 8, that only give you 256. In other words, what? Okay, the range you can go is only within 256 locations. So, but because it's signed, so it can be positive or negative. So the range in both positive and negative what is this range, from negative 128 to positive 127, including 0 here. So totally gives us 256 values. So when we represented this range in hexadecimal, which is 80, and 7F. That's what a short branch instructions. When we have long branch, okay, so the offset can be 16 bits. So again, in sound value, it's 16 bits. So because 16 bits, so we have 65,536 memory locations we can go. So because it's signed, so we have half a half. So this is a range we can go. So we can move forward to what? To 32,767, or move backward for the 32,768. 0 right here is where you state now. It's the value of program counter now. So all these values add into the current value of program counter that gives us a new location that's where we should go. CPU should go to fetch instructions. So for this range, if you represent in hexadecimal, that's 800 and 7FFF. But when we run a program, you can use either decimal or hexadecimal. Of course, a lot of people prefer the decimal. So this is what we have: the short branch and long branch. They all can run in the relatively address mode. So as I mentioned, those 8 bits or 16 bits offset, they're signed 2's complement numbers. Okay, so we can move backward or forward. We can move backward or forward. Of course, what if offset is 0? That means what? That means what? We execute the next instruction immediately following the branch instruction. Okay, no matter what's the test result. Okay, because what? Because if test result is true, then what? Then you branch to. But if after the 0, you branch to the 1 immediately follow you. If test result is what? Is false, is where you also should go. Sequential. So here, okay, in general, if you recall what we learned about the branch instructions, we mentioned what? We mentioned the branch node based on test result. A test result in general is based on we testing what? We testing the condition code register values based on CCRs. Remember, so most of them when we branch node, okay, we test if we meet a condition, okay, or not. Okay, if we meet a particular condition or not, so we mainly in this condition that shows the value. Okay, the based on the computation result, we passed in testing some values of a condition called register flags. Now, so as I mentioned a moment ago, for branch, okay, we can either for the offset here, the branch offset, it can be numerical value or can be label. Okay, now, however, if you use a numerical value, you have to remember these values. You have to find out what you have to compute this value, make sure it's correct. Okay, now, so if you use label like flag, then we simply what? Because label is much easier to remember, so it's very easy for us to program. So next time what? Whenever if you hope we branch to a particular instruction, then we label it. So we make what? We make the where we go. We make what? Offset to be labeled. The next time what? We label the instructions where we should jump to. Okay, so we simply call it here. We prefer to use label to serve as branch offset, okay, rather than numerical value. Because if you use numerical value, it's difficult. So you have to find out exactly what's the value it should be. So you specify a value there, okay, like this. So if you made a mistake, then what? Then your program will be wrong. So if you use a label as a programmer, it's very easy. You don't need to worry what's the value. Assembler will calculate the branch offset, okay, when a symbol that represents the branch target is met. So assembler will find out, okay, what's the value where you should branch to. So as a programmer, you only simply label the offset. Then you use this offset. You use this label to label the new instruction set you hope to branch to. So in our book, they give us example, show us about you can use numerical value. Like here we have, here we see a very good example. Here we go and label clearly. We have 4 fields. We have memory location, we have label, we have opcode. So this is the opcode here. This is opcode here. This is the opcode. This operand. So we have B and E. Branch if not equal. So in our book, they give us example. Assume now, okay, if not equal. So we do some testing here on top. Okay, if they're not equal, or when the Z is not as 1, then we branch is not equal. We branch to where in our book they give us example. They found this value need to be 10. This value need to be 10. Need to be 10. Okay, and then what? Then they found out what? If so, they should branch here. Let me see. And I'm sorry, it's 10 because here we add 10 into A02. So if you turn to page 54, we see the example, and then here the offset is what? It's 10. They use 10 here. They use 10 here. Why 10? Because this is distance from here to here. But this is where we branch to. So if you need to use numerical value, then you simply remove next. Okay, you have 10. If so, you have to find out, make sure, the memory difference mean the location at the IX. This is where you hope to go. Okay, is 10 memory locations away. But now, as a programmer, okay, in order to make our program easy, we prefer to use label. Okay, if we prefer use label, so let me clean this out. If you prefer use label, we simply say the word branch if not equal. So when we do some comparison, here we go. If they're not equal, we branch. We do some test here. Okay, if not equal, we branch. Where we hope to branch to, okay, we branch next. Next here is label. Then what? Then where's the label? Where's next? Okay, whatever you like to branch to, if not equal, assume right here. This is the way we should do. If not equal, we perform these instructions, not sequentially those, not those. So if not equal, we jumped here. We execute right here these instructions. So we don't care how far away from here, how many memory locations away from A0 to A012. Okay, yeah, like this. So actually when we finish this operand value is a program counter A02. So that's why we said if you add 10 to A02, you get A012. But here we use label. If you use label, then make everything very easy. Okay, So we said branch if not equal, well, if not equal, we branch next. So we go here this way, we go here this way. We don't care how far away from here. So when we jump here, we go CPU, we execute increment the value of x. So it's very easy. Always far away, we can do it. So this is going to make our program very easy. So always make sure relative address mode always work. Okay, only work for branch instructions. Or we simply call the branch instructions designed to run in the relative address mode. So always easy and good that we use label. Okay, here the next term of course is name. Okay, of course make sure that the label you choose is not any of the assembly directives and is not any of instructions. So you cannot say I'm going to branch to org, I'm going to branch to end, I'm going to branch to like our ABA. Then that's what that's not right. That's not and correct. So we get trouble when we do assembly process. So I want you guys read the example on page 53 and page 54 of the book, so you can understand a little bit more. So that's pretty much we prepared for lecture 10, and we focus on these two address mode, and they are index address mode and the relative address mode. And I show you some examples. These are very commonly used, especially when you run a long program. You can always make sure about the differences. Okay. So in comparison, those two index address mode and relative address mode. They are a little bit more complicated than the first four we discussed last time. So this is pretty much the contents are prepared for lecture 10. The next time, we will move to a much more advanced topics of assembly language programming. That's the topics covered in the new chapter. And also make sure we have another homework, which is homework 4, that designed for us to exercise the topics we covered about address mode and assembly directives that I want you guys to try. So that's it for lecture 10.